So welcome to the 75th anniversary of NASA Ames Research Center and the Directors Colloquia Summer Series. The moon, we see it every day when we look up, is our nearest neighbor, yet we know so little. The moon is an integral part of who we are and what created us. NASA Ames has had a few missions to the moon. But when you look at missions as a whole, NASA-based missions, there is a science goal to it. But to achieve that science goal requires a whole team of engineers, a team of scientists, a team of accountants, a team of educational outreach. It takes a whole team. Besides the science, we also push the envelope of the technology that is needed to do space missions. Those technologies also advanced our ability here on Earth. Today's talk, entitled Skimming the Lunar Surface for Science, the LADEE mission, will be given by Brian Lewis. Brian Lewis is a system engineer here at NASA Ames Research Center. He is currently the lead system engineer for the BioSentinel project and previously acted as the spacecraft system engineer and the spacecraft manager on the LADEE project. He holds a Bachelor's of Science and a Master's of Science in Mechanical Engineering from Utah State University with a focus on thermal systems engineering. He has been involved with spacecraft system engineering for over 14 years. Please join me in welcoming Brian Lewis.
All right, thank you all very much. It's an honor to be here today. It is a little bit intimidating being placed between Robert Zubrin and trying to lead in for Rusty Schweikert, but I'll do my best and try to give you some interesting things that we learned while testing, launching, and flying LADEE. Like Jacob said, I was the spacecraft systems engineer for a little bit, and then my last role on the project was as the spacecraft manager on the project. So I was, like Jacob said, focused mostly on making sure that the technologies that got our science instruments into orbit worked together when they were all brought together. As a little bit of an intro to the LADEE mission itself, the objectives of the LADEE mission were to measure the lunar dust and examine the lunar atmosphere. The LADEE mission was originally awarded back when we were still on a path to placing astronauts on the moon, and the science rationale was to try to characterize that thin exosphere around the moon before we landed astronauts there and landed rovers and started building bases and started disturbing that atmosphere. So we know what it was in a pristine condition. As you all know, we are now on a path on placing astronauts onto asteroids with the goal of getting them toward Mars. But a lot of the research that we learned and a lot of the science data that we took on the LADEE mission will help us understand what we're doing on that path there as well. So the science that we collected is still very useful. Some of the key parameters, LADEE itself was launched in late September or early September of last year, and then it impacted with the moon in about the middle of April of this year itself. The spacecraft itself is a small Explorer. It was about 300 kilograms. It was an enhanced Class D. The spacecraft was itself provided by Ames Research Center, and the spacecraft instruments were managed by Goddard Space Flight Center. But while those are said, that's not the whole story. In the end, we totted up all of the contributions from the different NASA centers and a lot of our partners. And 8 of the 10 NASA centers contributed directly to the success of the LADEE mission, as well as providing numerous small companies providing technologies that made the mission a success. The instruments we've flown, I'll talk a little bit more about later, but there were 3 primary instruments on there: a neutral mass spectrometer, an ultraviolet and visible spectrometer, and a lunar dust explorer. Those were all meant to characterize the exosphere around the moon itself. And then there was a technology demonstration payload. And that payload was a lunar laser comm terminal. We were trying to demonstrate the viability of laser-based communications from beyond low Earth orbit for the first time ever. And then as another first, the mission itself was launched off of a Minotaur V launch vehicle out of Wallops Flight Facility in Eastern Virginia. This was the first flight of the Minotaur V, and we had a little bit of birthing pains with that as well. Won't talk too much about them, but there were a lot of firsts that we did with LADEE, even though it was a low-cost mission. In terms of science objectives, I talked a little bit about these before. We were trying to determine the composition of the lunar atmosphere in an undisturbed state. Since we hadn't landed anything there for quite some time, we thought that this would be in a relatively pristine environment. And then we wanted to characterize that environment, measure its spatial and thermal and temporal variability, and the impacts that different things like the solar wind, the Earth's magnetosphere, impacts from meteoroids or asteroids would have on the lunar atmosphere as well. And one of the reasons that we wanted to do that was that we were able to take the science that we learned there and apply it to other small bodies around the solar system. Places like Mercury, the moons of Mars, the moons of Jupiter, small asteroids, all of these types of bodies around the solar system are surrounded by thin exospheres, much like the moon has. And so what we learned from this mission, we'll be able to use to characterize and inform our operations around those bodies in the future. The science payload, as I talked a little bit about before, you can see there on the top left, there's a neutral mass spectrometer that was provided by Goddard Space Flight Center. It measured a lot of the atmospheric constituents around the moon. Most of them were noble gases, as you can see, argon, helium, neon, things like that. But they were able to pick up and characterize a handful of other gases as well. There was an ultraviolet and visible spectrometer that was provided by Dr. Tony Colaprete here at NASA Ames Research Center, and a lot of the team I've seen filtering in here as well. That spectrometer works to characterize the species of elements that we see in the exospheric dust, whether they're things like sodium or potassium or other elements up in the atmosphere there. And it's done by measuring either the emissions or the transmitted light coming through the sun that is then attenuated by the lunar dust. And then lastly, there was a lunar dust experiment that measured in situ dust. It was actually characterizing the impacts of the dust particles as LADEE flew around. And those are the major elements that characterize the atmosphere, got the science. And I'll have a few charts later that'll talk a little bit about that. Our laser-comm payload, you can see here, was mounted on the side of the LADEE spacecraft. There were a couple of internal instruments as well, or internal components of that. This was, as I said, a tech demo. They weren't really sure whether this would work, and we thought that we would have to take a significant amount of time making it work, spend a lot of time trying to sync up the transmitter and its ground station. As it turned out, we were able to acquire with it on almost the first try that we had, and by the end of the mission, they were able to achieve over 600 megabit per second downlink and about 20 megabit per second uplink from the ground. This is orders of magnitude beyond what we've been able to do with RF-based communications in that regime. The Goddard team that worked on that with MIT Lincoln Labs is now working on trying to do another demonstration off the International Space Station where they can push these speeds into gigabit per second type speeds. But the nice thing that you can see is that we were able to do fully autonomous lockup, and we were able to do streaming video. It might not seem like a lot, but when we're sending astronauts out to the deep space environments, being able to allow them to maintain links with Earth, links with their families, links with people here, is a major part on being able to allow them to operate in the spaceflight environment for that long. So being able to demonstrate these type of capabilities is a huge benefit for extending astronauts into that deep space regime. In terms of the flight system overview, I have a nice little model here. I think a few people, Jim Cannon probably remembers this, Butler Hine, a few of the LADEE folks in here. This was what LADEE looked like probably about 5 years ago or so. And then on the screen here, you can see what LADEE looked like right before launching it. So you can see how it changed a little bit. It used to be 3 modules, ended up being 4 when we actually flew it. There was a nice thermal radiator on the top panel of the spacecraft that we were trying to keep open so we could reject as much heat to the environment as we could. And you can see in the end, we had to cover up a lot of that radiator with things like star tracker, baffles, and harness, and other devices. And there's a part of the evolution that we go through in terms of a system engineering process. When we started out putting the design together, we made our best estimates, our best guesses at what the mission would require. We placed those instruments down, and as this design evolved, we were able to go through and find all the supporting hardware that we had missed in the first time or the first cut that we'd done through the design. And so you can see kind of an evolution as the design progresses there. The spacecraft itself has an all-composite structure. It's a composite face chutes with an aluminum honeycomb core in it. And see here we have a single-stage bipropellant system, and I'll talk a little bit later about some of the challenges that we had in integrating that. They're all body-mounted solar arrays. We didn't deploy any solar arrays, and that was done to reduce risk, keep our costs down. We had about a 24 amp-hour lithium-ion battery. It's a fairly standard battery. They actually make those out of the small AA type cells that you would find in most stores around, and then they put a lot of battery charge protection and other circuits around it to keep the battery working functionally and working well over the life of our mission. We had an S-band communication system that would allow us to push about 128 kilobits per second down from the moon and about 2 kilobits per second up. And in that statement alone, you can see the difference in what normal RF systems and laser optical systems can provide. They're orders of thousands of orders of magnitude difference in the amount of data that we can get back, and that directly helps our astronauts and it also helps our science. We were limited in the number of science observations that we could take by the amount that we could transmit back. If we'd have been able to use that laser comm system for the life of the mission, we would be able to return a lot more data, and that's something we look forward to using in the future. So that's a kind of a summary of the system itself. The system was about 130 or about 300 kilograms and about 134 kilograms of propellant when we finally launched it. And so we get into now, Butler Hine, the project manager for the mission, came and gave a talk last year. That was just before we'd started to do most of this work and shipped it off to Wallops and launched it. And so we can see here, here's the route that we actually took when we were shipping LADEE from Ames Research Center out to Wallops Flight Facility. We started out here and we packed it onto a nice convoy. You can see we have a large truck there in the center and a lead car and a follow car. And we had about 5 or 6 of the people from the LADEE project itself. We had some people from Ames Protective Services. We had QA people traveling with it to make sure that what was going on was in accordance. And we actually had a couple of nice people that volunteered from the center to drive along with the vehicle itself, just because the team itself had a lot of other work to do. I think Yvonne Cagle and Dana Lynch and maybe a few others had made the trip out with us. A lot of the people that actually made that trip were younger people who had been on the project but had been working really hard and did it there. So one of the things, another key note that you'll see in going through this is that even if you're young and starting out in a new entry to the Ames system, you're given the opportunity to prove yourself and do a lot of things that actually make major impacts on these projects. You don't have to wait for 20 years before you can do something that's actually going to fly in space. You have a chance to do that from coming in. After we'd got the system all packed up and ready to go, we took one last picture, and this was seen as a very auspicious omen because you can see there in the thing, top center of it, you can see the moon. And then you can see our destination right as we're starting out our journey and see where we're shipping to. And this was seen as a great omen for the trip itself. And as we were driving along, you can see that our photographer along the way decided where we wanted to document the trip. And you can see us crossing over into the state of Arizona there. I didn't include a picture of it, but a few hours after starting off, our team ran into a small problem where one of our air conditioning units started throwing up an error, and they didn't want to continue if we weren't conditioned and had clean air and cool air in the vehicle. So they actually had to stop at Dryden Flight Facility and take and stop and repair that unit. Luckily, it turned out to be a wire that had kind of vibrated loose, and they were able to repair that fairly quickly and continue on their way. But it speaks to the challenge that you see that you didn't really plan for or expect, but all the things that you have to kind of have a contingency plan in place for. Continuing on, you can see that the moon in the background with LADEE traveling became a frequent focus of the pictures that our documenter decided to focus on. This was as they were crossing over from New Mexico into Texas. And then you can see here them pulling in on their on their midway stop into Amarillo, Texas. That was where the team stopped about halfway through and took about a half a day or a day break in the middle of their driving. And again, you can see LADEE with the moon up in the thing. I think our videographer was becoming a bit of a lunatic at this point. And that's the last really horrendous pun that you'll get for the day. Continuing on, after we left, I'll go back one of the items that we were concerned about. As we were coming into Amarillo, Texas, about 4 or 5 days prior, there was a string of very large tornadoes that had passed through Oklahoma City. Some of you may remember from last year, there was a lot of destruction. There was a lot of people that had lost houses. A few people had lost their lives and whatnot. And we were concerned about it, but by the time that we'd got there, the crews had cleaned up their route enough that we were able to continue on through it. But I know we had to consider whether we wanted to head north into Kansas or south into Texas or a few different things along those way. And the team itself and our protected services had to set up a lot of different waypoints or way stations where if we ran into inclement weather or something like that on the way, we could get LADEE into a resting space within 2 or 3 hours. So they had to do a lot of work in planning that route out. You can see here the next day they're starting to pull into the state of Virginia. As light came back up again, I don't have a lot of pictures from that point. I think our videographer became tired at that point and he stopped documenting quite as many places they went to. And then on the far side of Virginia, you can see we actually had to go through a tunnel, and we had to do a lot of planning to make sure that LADEE itself and the truck that it was in would fit through a tunnel on the way to the launch site itself. And then on the last picture there, you can see we finally arrived at Wallops Flight Facility on a nice somewhat cloudy day, but a very beautiful day. And LADEE was able to make that trip in very good time and with very good weather. We were actually very lucky with the weather along a lot of the stops on the mission. So when we got to Wallops Flight Facility, we had a few things that we had to do, and one of them is we had to spin balance LADEE. And this was a test or an operation that we were pretty nervous about. As you can see, we had to put LADEE in a large facility, get everyone out of there, and make calculations on how far back from the vehicle they needed to be in case something came off of it. Make sure that everyone was safe in operations and working on it. The reason that we had to spin balance LADEE like this is that LADEE was designed to spin while it's the fifth stage of the launch vehicle fired and thrusted it on its way to the moon. And so we had to make sure that it was very well balanced. For other operations, we had to make sure that that central thruster that you see down in the interstage adapter there was also very well balanced and aligned within about 2/100ths of an inch in order to make sure that we could meet the requirements that we had on operations. And so this test, the team got it up on the vehicle, put some ballast on it, and you can see here, they cut the video in half so we didn't have to watch all of it. But it got up pretty fast. This was about on order of what the spin rate of the vehicle was while it was doing its mission. And that caused a lot of consternations and deep breaths and fun moments. And when we found that it was able to pass that all, we were all very happy. One of the key takeaways that you can see from it there, you can see a very blurry LADEE all around, and you can see our OCS, that main nozzle on the bottom. Very nice, very steady. You can see a perfect shape. They were able to balance that nozzle out extremely well, and the system itself performed over the life of the mission extremely well. Another fun activity was that the team decided to practice their YMCA moves. We have a great Y and an M, kind of a C. In order to fuel LADEE used a bipropellant system. The propellants on it were toxic, they're carcinogenic, they can cause birth defects. So in order to use them, you have to be trained up to use a escape suit, basically a spacesuit without some of the hard walls and radiation tolerance like that. A lot of the people that did this work too were also fairly new to the project, fairly new to Ames. You could argue that we were sending the interns in to do the dangerous work. I prefer to say that these individuals did excellent work throughout the mission and really worked hard and put themselves in a position where they were able to directly contribute to what LADEE was able to do as a success. Again, if you come here, we'll give you things that you can do right off the start. And then we transitioned into launch. Well, once we had it fueled and on the stack, we were able to launch it. It launched within about the first 10 seconds of its launch window opening. We had almost perfect weather for that. We were worried about hurricanes, we were worried about high winds, we were worried about clouds and thunderstorms. And the day of, the weather was almost perfect. You can see a photo from our team there from the Chincoteague area near the Wallops Flight Facility. It went beautifully. You can see here a view from New York City. I believe this is off of Rockefeller Center, and you can see the city there in the background. I know Dr. Warden said that he was mildly paranoid for several decades about ever seeing an ICBM on a trajectory over the eastern coast, but this is one that we were all happy to see. And then one of the more interesting views you can see is here from a suborbital amphibian. The Wallops Flight Facility team, in reviewing the camera footage that they were able to pick up from the launch, was able to find out, unfortunately, there was a small frog that was kind of picked up in a plume from the vehicle itself. Now, the launch site teams do a lot of work to try to scare animals around out of the way. They set off sirens, they have hawks and things like that that they try to get animals out of the way, but they don't always work. This is just one of those serendipitous moments where you see something that you could have never planned or intended. And we now allow the frog to join SpaceBat in our list of unintentional astronauts. LADEE's journey to the moon. You can see here after our launch, we had a plan that took us out on 3 phasing loops. And on each of those loops, we had to plan for up to 2 burns per loop. We were worried that the solid vehicle, the Minotaur V, since it was the first flight, we weren't sure exactly how well that would inject us into orbit. Turned out that it was almost perfect. Our orbit determination and launch team said statistically perfect is what the launch had provided for us. So we were able to cancel most of the actual maneuvers that we had planned. The one challenging thing about all of this, though, is as you can see the dates there, 9/13, 9/21, those were all during the government shutdown last year. LADEE's flight operations team was determined to be a mission-critical crew, so we got to come in and guide the vehicle and watch the vehicle as it was doing these steps, but we got to come into a ghost center. There was almost no one here. It was like coming into a zombie movie on the weekends and seeing no one around. But while we were able to do that, we were able to execute the 4 burns that put us into a nice trajectory to the moon. And then lunar orbit insertion was, the first burn was performed on October 6th of last year. You can see a summary of the burns down there in the lower right, but you can see the performance error on nearly all of those was less than 1%. The LADEE propulsion system worked very well due to the spin balancing and the structural design efforts that our team went through. There were a lot of questions about the LADEE orbit and why it took us as much effort as it took to put on it. This model is a model of the lunar gravity field that came off of the Grail mission. And you can see here they're showing the relative influence from one side of the moon to the other, and you can see mass concentrations. On the near side of the moon, you can see that there's not a whole lot. Looks like it's pretty mild. And on the far side, you can see some pretty big mass concentrations. And you can see that they're actually pretty spotty, north versus south. LADEE itself was in an equatorial orbit. A lot of the polar orbits are able to get away from some of these mass concentrations, but LADEE's orbit was perturbed highly. You can see a graphic of basically what it does here. As LADEE was traveling around, those mass concentrations on one side of the moon would essentially pull our perigee or periapsis in closer and push the apoapsis out a little bit farther from the moon. And so, as the mission evolved, we were forced to constantly perform maneuvers to correct our orbit, prevent ourselves from running into the moon, and prevent ourselves from drifting too far away to collect useful science from our instruments. And then you can see down there at the end, that relocated margin, that was time that we were able to put into science operations that we weren't originally booking. And that was due to the near perfect performance that we had from our launch vehicle and from our propulsion system during those burns. We were able to use the extra margin we had to return more science. Some of the science measurements we did, I'll get into these, LADEE argon measurements, these were returned by the NMS instrument. Apollo 17 determined a lot of argon around the moon, and it was not detected by the Lunar Reconnaissance Orbiter. The Lunar Recon Orbiter was a lot higher up than the Apollo 17 were. But one of the questions is whether that argon was really there, whether it was being brought in from somewhere else, or what was going on. You can see a kind of a schematic down in the bottom left hand about what the behavior of the argon was around the moon. When it was hot, you could see those argon molecules picking up a lot of energy from the sun, the solar energy incident on it, and being able to loft themselves up fairly high, tens of kilometers off the lunar surface. And then when they came down over the dark side of the moon, they cooled off fairly rapidly and bounced much lower and basically stuck to the surface. And then when they got back hot, they would pop back up again. And so you can see that pointed out in the graphics on the right, showing from the NMS team, showing where they measured the highest concentrations of argon. Now, there was a fairly large question at the start of the mission about whether this argon would be found in one place or whether it would diffuse all around the moon or not. If this diffusion action was fairly fast, then we would expect to see argon pretty much constantly around the moon, just whether it was hot or whether it was cold, you'd see more or less. However, we know that there is some argon-40 being generated as a result of the radioactive decay of potassium-40 that's in the lunar crust. And if that generation mechanism is faster than the diffusion mechanism, we might be able to find something that there was concentrated argon around the lunar surface. And what they actually did find was there is a fairly high concentration on the lunar surface. It's around minus 50 degrees latitude. It's around an area called Aristarchus, and there are some people working very hard to try to figure out why this is. About all that our mission scientists will tell us about this at the moment is that this location is special. We're not exactly sure why. We think that it has something to do with how the moon itself was formed, how planetology, how the planets are evolving, but they haven't been able to fully explain that yet. That's something that's still ongoing. Moving on to some of our other instruments. This is, I'll talk a little bit more about some of the operations. This instrument, UVS, was a little bit more operationally intensive. They had to put together a lot of different profiles about how we use their instrument so that they could get good data off of it. There's a couple of images here that talk about how data was returned. In this case, as we were coming back from behind the moon in the dark lit portion, they would turn on their instrument and take readings from the dark portion of the moon. And then as they were approaching the terminator, you can see the faint glow from the sun approaching. You could start seeing the actual dust particles in the atmosphere getting hot and emitting data. And so they were able to then use that to turn it into the data products on the right. You can see some of the rough data products on the top right. And in the bottom right, you can see the process data products. And so they'll take differences between the different measurements at the different points in time, and they'll be able to, in this case, point out that they're seeing a large amount of sodium at this measurement. And they'll be able to use those to determine what the constituents and the relative abundance of those constituents in the atmosphere are. UVS itself actually had several operating modes. I don't have time to go into all of them here, but a lot of them looked at how the dust attenuated the atmosphere as the sun was dropping down toward our horizon, or how it might be scattered by that, the dust in the atmosphere. But what they were able to do is map out a lot of sodium in the atmosphere. They were able to determine, as you can see from the bottom right, that sodium varies a lot with lunar phase. It increases toward full moon, but then as the moon enters the Earth's magnetotail, sodium production drops off drastically. And they haven't been able to explain that yet. The team is still working on that. They're still doing analysis, and there are ideas of it. There are some variations that suggest that other things such as micrometeorites or things like that might be influencing those, but the explanations for why they're seeing that change in sodium abundance will help constrain what we're seeing in other atmospheric or other planetary bodies around the solar system. Other items characterizing lunar dust. You can see here some of the measurements from LDEX. They recorded over 11,000 impacts over the mission. They were able to determine that there is a fairly large dust cloud, or fairly substantial dust cloud, that's sustained by bombardment from interplanetary particles. And interestingly, you can see that that's not actually toward the daylight terminator. The team itself is working on finding out why they determined or detected more at that angle. It's probably about 10 to 15 degrees off from the terminator itself. They don't have an explanation for it yet. That's still coming up. Moving on to a few other things. The orbit determination team was able to work extremely well with the data they were receiving off the mission. At some point, we were able to coordinate ourselves with the Lunar Reconnaissance Orbiter. We were moving at nearly 2.2 kilometers a second relative delta velocity. It's really fast, really hard to take pictures of that. But we were able to give them an ephemeris, or an estimate of where our position would be at some point. They pointed their main LROC camera at it and took a picture. And what you can see there's the somewhat processed image, and you can see what the vehicle itself lined up afterwards. Our team was able to determine our position fairly accurately over the entire duration of the mission. Star tracker images. We were able to use our star trackers as cameras later in the mission once we did some software changes. We were able to pull things off of them. You can see this is a sequence where we turned on the camera and started taking images as we were traveling over the lunar surface itself. And the camera images, while not wonderful, were still good enough for us to be able to determine a lot of the different features that we were seeing on the surface, different craters, different mountains, different ranges on the moon themselves. And you can see here's an animation. You can see the Pleiades running past on one side, and on the other side a collection from a different point in time. You can see right as we're coming toward the daylight terminator, the cameras themselves start trying to adjust their automatic gain settings to deal with the increased light coming from the sun, and you can see that the frame rate slows down significantly as they were doing that. But we were able to get pretty good data off of those over the course of the mission. That was one engineering product that we put together that we didn't expect to at first. Moving into some of LADEE's last days, you can see here was our prediction for altitude over the end of the mission. Using some of that extra propellant that we had, we decided to go for some really high priority, low altitude science. For most of the mission, LADEE's periapsis was down at the 35 to 40 kilometer type of range. And for this last portion of the mission, we decided to try to push that down into the 10, 5, and down into 2 kilometer type ranges to try to really determine whether the dust atmosphere and the argon concentrations changed at those lower altitudes. We also did have one high priority engineering test that occurred at some point here, and that engineering test was a 4-hour lunar eclipse. LADEE was never designed to operate through an eclipse of that magnitude, and at first it was thought that the system itself would freeze and die because of the eclipse. We were planning on impacting with the lunar surface prior to that date. With the on-orbit data that we were able to gather about how the thermal system and our batteries and our solar array system was performing, we were able to project that we would be able to fly through that. Headquarters gave us the chance to do so in order to try to collect some of this low-altitude science, and LADEE did successfully fly through that eclipse. We had to reconfigure a lot of our fault management so that the fault management system didn't shut off things when we didn't want them to, and we had to power off a few things just to sustain or conserve battery energy, but we were able to do that. After we did that test and we got ourselves back into our science orbit, our orbit determination folks came back and they did some measurements, and they found that the orbit that we'd placed ourselves into the last time had some pretty low predicted heights above the lunar terrain. You can see here there are two lines, one at 2 kilometers and one at 0 kilometers. LADEE had a predicted uncertainty in its altitude of around 2 kilometers. So when the team noticed that at some point we started dipping below that 2-kilometer uncertainty in what our altitude predicts were. And at that point, they said, we are in uncertainty range. Some of those passes might be impacts. And you can see here, some of them were actually predicted to be below 0 kilometers. Now that 2-kilometer uncertainty was a plus or minus 2 kilometers, so again, we were fairly hopeful that we might be able to live through this. But when we noticed this, we started making plans to monitor the vehicle and try to retrieve as much science data as we could during this time. And the team, in somewhat black humor fashion, decided to name these potential impact sites like you would hurricanes. And you can see Andrea, Bruce, Charlene, Derek, Aaron, Francis, and a few others. The naming convention that we chose was that none of these names could be of people on the actual ops team itself, so they couldn't be blamed for anything. But then we came into the ops center itself and started watching as this happened. And we saw Andrea at 1.44 kilometers actual over the surface, and that looks pretty close to that predict. And we saw Bruce at 1.2 kilometers, that looks like pretty close to that predict. We saw Charlene and Derek and Aaron at 1/4 of a kilometer over the lunar surface. And then we saw what we see here. And here we can see LADEE coming up, flying over and at the lunar surface in its trajectory, and you can see the Earth in the background. And what we were looking at in all these geometries was the Earth was fairly low over the horizon. And all of these impact times, or possible impact times, was right around the time that we would have lost communications with the vehicle itself. And so there was a lot of uncertainty about whether we lost the signal, whether it was from an impact, or whether it was just because we went behind the moon and just had lost signal. So you can see here, LADEE's flying along, and another item is that we generally tended to fly in this sideways orientation. And you can see here that we were watching it coming into the Francis configuration, a relative velocity of about 1.7 kilometers a second. And right as we came up, we lost signal with the vehicle. And we can see here, one of our main orbit dynamicists watching as that signal cut off, and you watch as 4.5 years of work stop talking to you in 1 second. And you wonder, was that it? Or did we luckily make it over the surface? And to date, we've never heard anything more from LADEE, and the orbit determination predicts show that we did in fact impact the moon at a site on the outer eastern rim of the Sunman V crater, and the coordinates are there at about 11.84 by minus 93 lunar latitude and longitude. So if you want to go look at it, you can actually see where those are on a couple of different mapping sites. That impact site actually is on an area of the moon that actually librates back and forth. And so you can see that impact site at certain times of the year, and at certain times it's actually on the far side. So there is a schedule that's out and published about different times that you can find those impact sites. So you can actually look at that with ground-based telescopes and see if you can find anything fun and see LADEE's final resting place. So that was my experience of flying LADEE. Now, a few of the other things that I was asked to talk about today. Well, what's next? As Jacob showed about and talked a little bit about, one of the next things that we have is called BioSentinel. BioSentinel is a 6U autonomous nanosatellite. It's a little bit bigger than most of the CubeSats that we've flown. There's about a 4U microfluidic biology payload in there. We take micro wells, we fill them with yeast, and we specially tailor the strain of yeast that we have to look for radiation damage in the yeast cells. And we can correlate radiation impacts to growth in the actual yeast cells. And what we can do is extrapolate that to the rates that radiation impacts might have on astronauts that are out in the lunar environment or deep space environments as well. But one of the challenges here is that we have to reserve, with that 4U bio payload, we have to reserve about 2U for the bus, attitude control, radios, GNC gear, everything else. All of the complexity that we had in LADEE in a 350 kilogram bus, we're now trying to cram into a 14 kilogram bus. Doesn't do quite as much, but all of the functions need to be there. And so this is a real engineering challenge to provide some of the data that our team needs. For that, sometimes I like to jokingly call this the BS mission. I like the acronyms or the initials there. But since we're also taking yeast and growing yeast in space, I also like to call this the BeerSat mission. I don't know, I think that one's a little more poetic name personally. BioSentinel itself is going to be launched off of the Space Launch System. It's the next iteration of the large uncrewed vehicle, or the large crewed vehicles will be taking our astronauts to the moon, to deep space targets, asteroids, to the Mars eventually. This will be a secondary payload. The orbit itself is still to be determined, But right now, preliminary indications show us I'm going into a slightly Earth interior orbit, a 0.98 by 0.92 astronomic unit orbit. One of the big challenges we have there is that we have to rely on things like star trackers for control. There's no magnetic fields. We have to have propulsion, as there's no magnetic fields to help us out. And our ranges from Earth are extremely long. At the end of our nominal mission, we'll be about 40 million kilometers from Earth. At the end of our extended mission, we'll be about 110 million kilometers from Earth. This is orders of magnitude farther than LADEE was, and it's a major engineering challenge. So this is something that we're working on right now as a project here at Ames. Getting a little bit into something else, Jacob and Jamie asked me to talk a little bit about, well, who am I, in addition to just what I'm doing here. A lot of the things that I like to do around after work and after my after hours is play a lot of sports. I'm on about 2 softball teams, coach one of them. You can see here's one group of there. That team is a Mountain View City League team. About half the team is NASA, about half the team is not. And there's a handful of people from the team here in the room. I used to play on a couple of indoor soccer teams. I used to run distance. There's me in a half marathon. About a year and a half ago, I was playing on one of those indoor soccer teams and was kicked in the side of the knee, and it destroyed my anterior cruciate ligament, my medial collateral ligament, and my meniscus. So I'm currently working my way back into being able to do some of those things, but I'm still back into playing softball at this point. Other things that I enjoy are concerts. And as part of those concerts, I have great fun with Costume Day. I don't know how many of you have been able to see Dr. Warden with some of his magnificent costumes, but I rather like the idea and try to do so myself. Path to Ames. How did I get here? I know Jacob talked a little bit about it, and it's kind of interesting that we have a group of Idaho students here. I'm from the small little town of Blackfoot, Idaho, off on the eastern side of the state. It's a town of about 10,000 people. As you can see, it's a town of some very rugged beauty, but not a lot of people, and we have a joyous potato museum. It's world famous. If you go there, you get a free potato. If you're on your way to Yellowstone National Park, you can get free dinner. I was there for the first 18 years of life, and then I decided that I was going to go to school, and the school that I hit on is in northern Utah, in a small town called Logan, a town of about 25,000 people, so I was stepping up, but stepping up very slowly. And as you can see, there's still some rugged beauty in that area. This is the Utah State campus, and you can see it's right on the edge of the mountains, and off in the mountains you can see ski resorts, rivers, hiking, biking, all things that I availed myself of. But the real reason I went there was that school had flown more student payloads as gas canisters, getaway special canisters on the space station or on the space shuttle than any other university had at that point. At that point, I already knew that I wanted to be involved with the space program, and so I went there. And I did 7 years at Utah State, working on a lot of thermal control systems, a little bit of attitude control and things like that. After that, I promptly followed up on all of that space training by going to Germany and working on robotics. Didn't do anything with space at all, but I went to the town of Siegen. Siegen is a small city of about 150,000 people. Again, you can see the general pattern of stepping up and stepping up slowly. And Siegen is between Frankfurt and Cologne, about halfway, and I was there for about 9 months working on haptic robots. That robot had a handful of sensors on there that would detect if you were getting close to objects, if you'd nudged them, if you'd bumped them, and it would put a lot of feedback into a joystick or into a headset, things to allow you as a remote operator to figure out how you were interacting with the environment around you. I got done with that. I tried to stay there, but they didn't have too many jobs at that point. So I ended up coming back to the States and going to a group called the Aerospace Corporation. They're down in Los Angeles, California. And I got sent out to help a lot of other people around. I worked with the Air Force on the GPS-3 program. It's one of the world's best clock radios. It is a clock radio. It's very cool, but it's not the most cool thing. I also did a lot of work at JPL, working on things like JIMO, the Jupiter Icy Moons Orbiter, that was trying to take a nuclear-powered spacecraft out to the moons of Jupiter and use a lot of electric propulsion to move around between the different moons. I actually worked as well on the Mars Science Laboratory, a little bit on the initial concept studies. What did it look like? What was it going to do? Was it going to have in situ resource utilization? Was it going to have other chemistry, biochemistry payloads? How were they going to land it? Were they going to use the sky crane or a larger aeroshell? I was involved with the project way back then. And then we decided that it was going to be on LA versus San Francisco. I met Pete Klupar, a handful of you know him, that was working at the center at the time, with Dr. Warden, and said, we need some people who can help us write proposals about small satellites. And so I came up and worked on L-Cross, and worked on LADEE, and worked on TESS. TESS was a follow-on that is still being worked on. It's a follow-on to Kepler. It doesn't look quite as far away as Kepler does, nor does it look for quite as long, but it looks at a lot more stars in the night sky around us, looking for exoplanets around a lot of things in our near solar neighborhood. So these are the kind of things that I've worked on that wonderful long path and winding path around there. And so that is all that I've got for you to do, and I hope that that's been an entertaining talk, and I hope you've learned a little bit more about the LADEE mission.
So we have time for a few questions. Please raise your hand, wait for the microphone, and when you get it, please stand up and ask the question.
A couple back here, one here. Oh.
If I remember correctly, and correct me if I'm wrong, the Chinese had put a lander down while LADEE was up there. Did you see anything?
Yes, that's right. Chang'e landed right about middle of the way through the mission. There is still a lot of work going on with the science team. They were able to see something happen about that time. The problem was that there was also a meteor shower right at about that time. So it's very difficult for them to try to disambiguate whether the increased dust and the increased material that they saw was due to the Chang'e lander or due to the meteorite shower at that point. As far as I know, they do not have any conclusive findings one way or another, but I know the team is hard at work on it.
I was just wondering, when you did the spin testing, did you have to actually make adjustments, or was it already in balance?
We did have to make adjustments. We did have a handful of ballast sites that were down on the bottom of the vehicle that were internal to it, but we also had some ballast sites that were up at the top of the vehicle on the outside. And we came in with an initial set of predictions of what the vehicle would need to balance it off on its final spin. The video you saw there was actually from the second test. We spun it once, made a set of updates, put the final ballast masses on there, spun it a second time, and I believe the second time was close enough that we were able to go with those ballast sites for the final flight.
Thanks, Brian. Two questions: engineering question, science question. Engineering question: did you have to account for the truck trip in your shock and vibe testing, or was it? And then the science question is: one of the things that was used to justify LADEE long ago, when it was just a concept, was the fact that some of the command module pilots in orbit around the moon during Apollo saw these streamers before sunrise. And I know LADEE didn't have like high dynamic range, high res cameras, but did LADEE or anything ever verify those streamers?
Okay, so both of those are very good questions. The first one, yes, we actually did have to envelope all of our transport conditions in the analysis and the testing that our mechanical team did. We had originally scheduled a test. It's kind of an aggressive test called the sine burst test, where we were going to take the LADEE structure with a lot of mass simulators on it and shake it pretty violently on a mass simulator table. We actually had a failure because of that. We then switched to an alternative qualification method where we used a lot of static loads that you could apply on the ground and did a lot of analysis based on the results that we got from those static loads to show what it would respond to. But yes, the transport loads were part of what we had to prove that the vehicle itself would withstand. We didn't have to do specific testing for it, but the loads and the analysis had to encompass it. For the second part about whether we actually saw those dust streamers or dust glow, the science team is still working on that. I don't believe they've published anything conclusive one way or another. I don't want to speak on that one because I don't want to say that yes they did when they didn't, or vice versa. As far as I know, there's still analysis going on, and it is still unknown. So sorry, I can't answer that any better for you. Other questions? All right, that looks like about it. Thank you very much.